Yes.
Yeah. Okay. So, hello everyone. My name is Lorenzo Ennoggi. I'm a PhD student at the Rochester Institute of Technology. And today, and thank you for having the possibility to speak, by the way. And I want to tell you something about binary neutron star merger simulations with Spritz. So, first of all, as you know, BNS mergers are multi-messenger events which involve multi-scale and multi-timescale physics. And so different codes, different approaches are needed in order to simulate different phases of the BNS evolution. So this is the whole purpose of the TCAN, right? So the typical workflow we follow for a full BNS run in the TCAN collaboration is this. So we construct initial data with Lorraine. We evolve this data either with Illinois GRMHD or with Spritz, which is the code I use. And then we hand off this data to HARM3D plus Nuke for the post-merger evolution. I will be mainly focused in this talk on magnetic field evolution in BNS simulation with Spritz. So let me tell you something about the code. So Spritz is a fully GRMHD code, which is designed to be a thorn in the Einstein toolkit. And it will be hopefully included in that at some point in the future. And it features a staggered vector and scalar potential evolution in ideal MHD. And it supports ideal fluid or polytropic EOS, as well as tabulated EOS, which typically depend upon res mass density, temperature, and electron fraction. It also supports electron fraction advection and neutrino leakage with Zelmani leak. Let me also point you to some key papers about the code. So we have the paper by Cipolletta et al. 2020, which basically describes the basic features of the code. Then we have Cipolletta et al. 2021, which describes, so introduces the tabulated EOS treatment and neutrino leakage, basically. And then we have a paper, which is in preparation now by Kalinani et al., which basically involves a new conservative to primitive scheme, which is going to be implemented in Spritz. And I point you to the talk by Jay Kalinani, which I think will be tomorrow, if I'm not mistaken. Okay, so as I mentioned, Spritz features a vector potential evolution in order to solve Maxwell's equation. So we start with a electromagnetic force potential, which is written in terms of a scalar potential and a vector potential. And we have a time evolution equation for the vector potential, which contains a flux term, which is basically an electric field, and a gauge term, okay? And the magnetic field is not directly evolved, but rather is computed as the curl of the vector potential. And this ensures that the solenoidal constraint is fulfilled at all times during the evolution, up to machine precision. So because you have a gauge term here, you have to choose a gauge, right? So currently in Spritz, 2 gauge choices are implemented. The first one is the algebraic gauge, which means setting the gauge term to 0. But this is found to be, let's say, not very suitable for BNS evolutions. So this is the reason why we also implement the generalized Lorentz gauge, which is basically a Lorentz gauge with a damping term on the right-hand side. And if you choose this latter gauge, you also have to solve a time evolution equation for the scalar potential phi, which is this one. And as I mentioned before, so in Spritz, electromagnetic variables are staggered. And this means that at the center of the numerical cell, we have the hydro and the metric variables, while the magnetic field lives at the faces of the cell, the vector potential lives at the edges, and the scalar potential is at the vertices of the numerical cell. And this has a big advantage over a non-staggered evolution, because as you see in this figure here, in blue, you have a non-staggered scheme, which gives rise to large post-shock oscillations, okay, which are removed essentially by staggering. And if you adopt a non-staggered evolution, you typically need to impose some kind of Kreis-Holliger dissipation on the potentials. And this was done in Whiskey MHD, which is the code upon which Spritz is based. Okay, so let's get to some results. So here I want to show you a movie about one of the first BNS runs I performed with Spritz and with generalized Lorentz gauge. And this is an equal mass system with ideal fluid equation of state. You will see the norm of the vector potential and the norm of the magnetic field. And you will see that the vector potential is advected toward the boundaries, which is expected. But you will also see a big numerical instability in this run. So let me play the movie for you. So you see in the vector potential, there is a large growth there is a large growth in the vector potential here, and a corresponding, let's say, spurious magnetic field all around the grid. So why does this happen? To answer this question, we analyzed the evolution scheme we adopt for the generalized Lorentz gauge. So as I mentioned before, you have to solve the two time evolution equations for the potentials, and then so the electric field term is treated by a high resolution shock capturing technique, and will be, let's not focus on this for now. Let's rather focus on the gauge term and on the derivative term in the scalar potential evolution equation. These two terms are derivative terms and are approximated by finite differences. And let's focus, for example, on the scalar potential evolution equation. So the scalar potential, as I mentioned before, lives at the vertices of the numerical cell. So the right-hand side of the equation must be evaluated at the vertices as well. So if you are to approximate this derivative with, for example, with a first order finite difference, you want this term here, fj, to be evaluated at cell edges, right? So that the derivative is computed at the vertex, which is between those two edges. But if you look at the expression for f, for example, it contains, for example, the lapse, okay? And the lapse is a metric related variable, so it lives at the center of the cell, and you have to figure out its value at the edge, okay? And this is, you can, for example, interpolate the values from the center of neighboring cells to the edge, which is shared by these cells, okay? So that's why I'm speaking about interpolation scheme, okay, in this sense. And you can choose whatever scheme you want in principle. And the first scheme, the one which was used in the previous movie, and the first one which was implemented in Spritz, was this one. So we interpolated psi MHD, which is basically the scalar potential, to the center and the vector potential to the center, and then computed f and g at the centers, and then interpolated back f and g to the edges and to the vertex. And then we took finite differences and subtracted the damping term, which is this one. Okay, and this scheme gave rise to that instability you saw before. So we decided to switch to another scheme, to a different scheme, which is partially inspired by the one used in Illinois GRMHD. We interpolate the determinant of the spatial metric and the lapse to the edges and the vertex, the vector potential from the edges to all the other edges, okay? The inverse metric and the shift to the edges, and then we compute the contravariant component of the vector potential at the edges. We compute the update terms as before, and as before, we take finite differences of f and g and subtract the damping term. So with this new scheme, the evolution is much more stable. It is stable up to merger. However, just after merger, you will see that another kind of instability arises. Okay, so You see that everything is fine up to now. So I apologize for this movie being a bit long, but okay, and if you okay, you see, let me stop the movie for a moment. Okay, you see these spots in the potentials, which translate into kind of, yeah, spots also in the magnetic field. And these spots remain fixed over the grid and don't go away. So there is a problem, right? And so, yeah, there was an improvement, but what to do at this point? So the first thing we tried was to interpolate the conformal metric rather than the physical metric. So the conformal metric is defined by these expressions, where psi is the conformal factor of the BSSN evolution scheme. And we decided to interpolate either psi and alpha, or alpha psi square and alpha divided by psi to the 6. You will see why we chose this variable in a moment. So interpolating these variables to the edges and the vertex, the vector potential to the edges and the vertex as well, the conformal metric this time, and the shift to the edges. Then we compute the contravariant component of the, let's say, conformal vector potential at edges. We calculate the update terms, which contain the terms alpha divided by psi square, alpha psi square, alpha divided by psi to the 6, sorry, and alpha psi square, which were the variables we interpolated before. And then, as before, we take finite differences and subtract the damping term. Unfortunately, interpolating the conformal metric gave no substantial improvement over the interpolation of the physical metric. So let me show you maybe just one movie for the magnetic field. So you see that interpolating the physical metric or the conformal metric in either way, okay, gives no substantial improvement, right? The situation is quite similar in all the three cases. And so the second attempt was to add a bit of Kreis-Holliger dissipation on the evolution of the potentials after merger, okay? And in this way, the instability is resolved, basically. Obviously, the price you have to pay is that you cannot resolve, for example, Kelvin-Helmholtz instability, the MRI, if there are, you cannot resolve that very, very well, but the evolution is otherwise much more stable, and this is probably going to collapse just after this last frame, okay? So it is about to collapse. The last attempt, which is in progress, is simply to reduce the Courant factor from 0.35, which was used in the previous simulations, to 0.25. And yeah, so to summarize, we saw that different Lorentz gauge interpolation schemes give rise to very different results in terms of stability, and that although there was a great improvement in the Lorentz gauge evolution in the past few months, more stable implementation is needed. And the plans for the near future are these ones. So the ideal fluid BNS run with dissipation after merger is basically ready for handoff to HARM3D plus NUC. Then we want to do the same run plus handoff without dissipation once a more stable Lorentz gauge scheme is available. And then we also want to run a tabulated equation of state simulation. To conclude, any helps, tips, discussions, maybe for the afternoon about the Lorentz gauge implementation would be greatly appreciated. And thank you for the attention.
Thank you, Lorenzo. If there are questions, please raise your hand. Okay, Wolfgang.
Just a quick detail question. So if I remember right, some versions of Spritz computed the curl of A in a way that uses one-sided differences at interprocess boundaries, for example, or outer boundaries. So I was wondering why these instabilities occur, exactly where they occur. Could it be that this is sort of related to this kind of boundaries and the reduced order of the finite differences for the curl at this place?
That's a good point. It could be. It could be. Yeah. Yeah. Thanks for pointing this out. Actually. Yeah.
Okay. Tzvi?
Hi, very nice work. I'm sorry I don't have suggestions about what to do with the gauge that you're discussing, but I have a question to both speakers in the last two talks. If we ignore the magnetic field and we just choose hydro, was there any attempt to compare the two simulations and see how, if the results are consistent at this stage, even without the magnetic field? Because I understand that basically they should calculate exactly the
Yeah, so I haven't performed any pure hydro simulations. I remember in the past someone performed those with Spritz. I think maybe Federico Cipolletta, but since he's here, I think he can confirm or correct me if I'm wrong.
Yeah, Lorenzo. Yes, that is correct.
Okay, yeah. And I'm not sure. So we haven't compared really apples to apples because we use a slightly different grid setup, and also, so I don't know. I don't think we've never done apples to apples comparison. No. It would be
well, this
interesting
is
to
something that I suggest that should be considered in the in the near future, because and actually doing just the hydro comparison at this stage will also be informative, because the whole, I think that the whole point of using two codes is to have some redundancy, and instead of doing the redundancy after we transfer the results to Harm 3D and seeing what the result of the final result, it will be better to make the comparison just before they are transmitted, the handoff is there.
Yeah, that's a good suggestion. Thank you.
Yeah. There is an entire working group actually dedicated that was created like this a couple of years ago to this.
So I encourage this working group to be more active.
Okay, thank you.
Okay, are there other questions? Okay, we do have a little bit of free time